And when you're looking for the surface area of a pyramid, for any pyramid, you're dealing with just a single base, so it's the area formula for the base. Okay, plus, and now you'll just take the sum of the surface areas of the lateral faces. Okay, so here you would add them individually. Now, what shape are these lateral faces going to be for a pyramid? They'll always be triangles. Okay, so there's not a specific formula to use on this. It'll be determined by what the actual base figure or the solid looks like. The example that I'm going to give you is going to be the following. If you had a triangular pyramid with a base that is an equilateral triangle. Bless you. Okay, so here's your base, and it's connected to a single point. And you're asked to find the surface area of a triangular pyramid with an equilateral triangle base. Okay, with the sides that are 6, so each of these sides measure 6, and its height of the solid itself, 10. Okay, so you know that the height of this whole solid here is 10. Can you figure out what the surface area would be for this? And again, I'll talk through this case. All right, what makes this a little more challenging is that the pyramids will tend to be the problems that you're going to have to use some other properties to determine missing measurements. So if we looked at the surface area on this, we have a base plus the triangular faces. In this particular case, since each of the sides of our base are the same length, we actually have 3 lateral faces that are identical. That's not always going to be the case, but for this particular example it is. And so what we can do is we can find the area by taking 1/2 base times height of our base, and then taking the sum of the 3 triangular lateral faces. So it's each of them given by an area formula of 1/2 base 2 height 2. So here's the equation that we're looking at. So it's just a matter of finding these values or measures. Okay, so let's start with the base. What if we take a top view of our base? Now, it's probably going to be helpful to look at a top view of this, okay, where each side is a length of 6. Because when we plug in our equation, we have 1/2 the base of 6, and its corresponding height, we would need to draw that in. Okay, well, how would we find what this corresponding height h is equal to? What kind of a triangle is created here? It's a 30, 60, 90 when we draw in that altitude. So if the hypotenuse is 6, what's the length opposite 30 degrees? 3, and then what would be the side opposite 60 degrees? 3√3. So there's our height, 3√3. We could plug that in. So we have the first part of our surface area done, the area for our base. So all we're left with is we have this 3 times 1/2 times our base and our height. Well, what is the base of this triangular lateral face? It's also 6. Okay, so all we need to do here is we need to find what is this corresponding height. We'll call it h2. Okay. So in looking for h2, the way that you would need to manipulate this is you need to imagine the height of your whole solid going straight down into the center of this triangular base. And then if you connect that to the point where the height or altitude of your lateral face is, what you see is it's going to form a right triangle right here. So what we need to do in order to find H2, so if I pull this triangle out, here's H2, here's the value I'm looking for. I know that my leg, my vertical leg is 10. I need to know what this horizontal leg is. Well, we go back to this top view. The unique thing with an equilateral triangle is this intersection point, which will be the very middle of your base, is also every point of concurrency that you can have in a triangle. So it is the centroid. And a centroid cuts this median into what ratio? 2 to 1, or the smaller, this closer part is 1/3 of the whole thing, right? So if our whole thing was 3√3, this distance right here corresponds to this portion. So what fraction of the whole thing is that going to be? It's 1/3. So 1/3 of 3√3 is just √3. So this length will be a √3. Okay, so you actually had to create that measure on your own. And then it's just a matter of solving. So we can use Pythagorean theorem. √3 squared plus 10 squared is equal to h2 squared. When you simplify, 3 plus 100 equals h2 squared. Combine your terms, extract the square root, and you get h2 to equal √103. And so that's going to give you your final piece of the equation for that total surface area. Okay, now, as you go through to calculate this, we can simplify it a little bit further. Half of 6 is 3. 3 times 3 gives us 9√3. Here, half of 6 is 3. 3 times 3 is again 9. Times √103. The units are unnamed, so it's square units. We are still dealing with a surface area, or a two-dimensional area.